There's a famous principle in quantum physics that, well, really shook the foundations of science. A principle that says we can never know everything about the smallest building blocks of the universe. It's called Heisenberg's uncertainty principle, and honestly, it's one of the most profound ideas in physics. But what does it really mean? How does it work? And why is it so important? Welcome to Großdenken, my friends. In this video, we'll break down the uncertainty principle step by step in a simple, clear, and scientifically accurate way. Before we start, let me remind you to support this channel by subscribing. It would mean a great help for me. Okay, now let's dive in. At its core, the uncertainty principle, formulated by German physicist Werner Heisenberg in 1927, is a fundamental concept in quantum mechanics. It states that there's a limit to how precisely we can simultaneously measure two related properties of a particle, such as position, where it is, and momentum, which is how fast it's moving and in which direction. The more accurately we measure one, the less accurately we can measure the other. This isn't due to flaws in our measurement tools, this is an inherent property of nature itself. To put it simply, you can't pin down both where a quantum particle is and how fast it's moving at the same time. But why is that? Let's take a closer look. The uncertainty principle is described mathematically using the following equation. Delta x times delta p is greater than or equal to h bar divided by 2. Here's what this means. Delta x is the uncertainty in the particle's position. Delta p is the uncertainty in the particle's momentum. H bar is a very small constant called the reduced Planck's constant. This formula tells us that the product of the uncertainties in position and momentum can never be smaller than a specific value. For example, if you try to measure a particle's position very precisely, making delta x very small, the uncertainty in its momentum, delta p, will increase. Similarly, if you measure the momentum very precisely, the particle's position becomes, well, blurrier. This isn't just a mathematical trick, it actually reflects the reality of how particles behave on the quantum scale. To understand why this happens, we need to talk about wave-particle duality, which is really one of the fundamental ideas in quantum mechanics. Particles like electrons and photons actually exhibit both particle-like and wave-like behavior. When we think of a particle as a wave, its position isn't a single point. It's kind of spread out across space, like ripples on a pond. The more localized the wave, so the more you pin down the particle's position, the more uncertain its wavelength becomes, and wavelength determines momentum. This is a direct consequence of the mathematics of waves. The tighter you squeeze a wave to determine where it is, the harder it becomes to determine its frequency or wavelength. In other words, the uncertainty principle arises naturally from the wave-like nature of particles. Let's visualize this with an experiment. Imagine you're trying to observe an electron using a high-powered microscope. To see the electron, you need to bounce a photon, a particle of light, off it. But here's the problem. If you use a photon with a short wavelength, which means high energy, to get a precise image of the electron's position, the photon will actually transfer some of its energy to the electron, changing its momentum. On the other hand, if you use a photon with a longer wavelength or lower energy to avoid disturbing the electron's momentum too much, you lose precision in measuring its position. This unavoidable trade-off is exactly what Heisenberg's uncertainty principle describes. The act of measurement disturbs the system in a way that limits how much we can know. Now, let's clear up a common misconception. The uncertainty principle does not mean that particles are fuzzy or that everything is random. Instead, it tells us that there are fundamental limits to how much information we can obtain about certain properties of particles simultaneously. The particles themselves aren't uncertain. Our ability to measure them is constrained by the laws of quantum mechanics. This isn't about our tools being imperfect, it's about the very nature of reality at the quantum level. The uncertainty principle isn't just a theoretical idea, it has real-world implications that shape modern technology and science. For example, quantum mechanics and chemistry. The uncertainty principle explains why electrons don't collapse into the nucleus of an atom. Without it, atoms, and by extension matter, wouldn't exist in a stable form. Quantum tunneling. This phenomenon, where particles pass through barriers they shouldn't be able to cross, is used in technologies like semiconductors and scanning tunneling microscopes. Quantum computing. Quantum computers rely on principles like superposition and entanglement, which are deeply connected to the uncertainty principle. These applications highlight how understanding quantum uncertainty has revolutionized science and technology. The uncertainty principle also raises profound philosophical questions about the nature of reality. Does reality exist independently of measurement? Or does the act of observing the universe fundamentally change it? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that reality is shaped by observation, that particles don't have definite properties until we measure them. Others, like the many worlds interpretation, propose that all possible outcomes of a measurement exist simultaneously in parallel universes. While we may not have definitive answers to these questions, the uncertainty principle reminds us that the universe operates on rules that challenge our intuitive understanding of reality. So what have we learned? The Heisenberg uncertainty principle tells us that there are fundamental limits to what we can know about particles at the quantum level. This isn't a flaw in our tools or experiments. It's a deep and intrinsic feature of nature itself, arising from the wave-like behavior of particles. This principle has not only shaped our understanding of the quantum world, but also led to groundbreaking technologies and deep philosophical questions about the nature of reality. What do you think? Does the uncertainty principle change how you see the universe? Let me know in the comments below. And if you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating insights into the mysteries of quantum physics. Until next time, stay curious, keep exploring, and remember, the universe is stranger than we can imagine.